this video is going to just talk to you a little bit about the empirical rule, which is found on page 683 of your textbook in section 9.4. And I'm going to be using the example that they also have regarding the lifespan of Batmobiles to kind of talk you through how to do a little bit of this. The empirical rule is specific to only the normal distributions, which are your bell-shaped and symmetric graphs. If you're not bell-shaped or symmetric, this does not apply. And these are approximations. When you get into statistics, you will learn a more precise way that's rooted in calculus that will help you get the precise percentages, but this is kind of a rule of thumb. 60% of all the scores in your data will be within one standard deviation of the mean. Approximately 95% of all the scores in your data are going to be within two standard deviations of the mean. And approximately 99.7% of all scores are going to be within 3 standard deviations of the mean. So to visualize this a little bit, I'm going to take the information about Batmobiles, I'm going to put it onto a bell curve. So we're going to assume that the lifespan of all Batmobiles has been found to be bell-shaped and symmetric. What we know about symmetric graphs is that the center is exactly where the mean is going to be located. And so that measure of center that we learned about in section 9.3 is going to be labeled right in the middle of that number line. So we have the mean labeled here in the middle as 9 years. The way that this works, because it is a number line, is that we use the standard deviation number as our ruler. We use it as our measurement forward and back to get other labels onto our graph. So if we wanted to go forward 1 standard deviation, if our standard deviation is 2 years, moving forward implies that your values are going to be getting larger, and so we'll be performing addition. If we want to go behind the mean or backing up a little bit, those values need to get smaller, and so we want to perform subtraction to get those values. So if we wanted to go from the mean forward 1 standard deviation, which would be 2 years, we would take 9 and we would add 2 to that. That would give us the next label for our first tick mark above the mean would be 11. If we were to go forward another standard deviation from there, we'd be moving forward another 2 years, and that would put us at 13 years. And if we go forward even one more, so 3 standard deviations altogether, we would be adding yet another 2 years to that, putting our last value at a 15. So 1 standard deviation above the mean is 11, 2 standard deviations above the mean puts us at 13, and 3 standard deviations above the mean puts us at 15. This symbol here that I'm using is the Greek symbol sigma, and it means standard deviation for a population. And so I'm just writing 1 sigma, 2 sigma, 3 sigma, so I can keep track of that. If I were to go from the mean and go in reverse and back up, go below average, my values need to be smaller, but I'm also, again, moving in standard deviation. So I'm going to back up 1 standard deviation, so I'll use -1 sigma. So I have to take my 9 years that's in the middle and subtract 2. That's going to put me at 7 years. If I want to go back another standard deviation, so now a full 2 standard deviations from the middle, I have to back up another 2 years, so it's going to put me at 5 years. And if I go that final standard deviation, going 3 behind the mean, I'm going to have to back up another 2 years, which will put me at 3 years. The way the empirical rule works is that it sections off that portion of the bell curve using those matching standard deviation values forward and back. So if we went forward 1 standard deviation and back 1 standard deviation from the middle, that's going to section off what the rule is saying is 68% of your data. So 68% of our data should fall between a 7 and an 11. So approximately 68% of Batmobiles have a lifespan between 7 years and 11 years. If we move forward 2 and back 2 from the middle, we're going to cover more of that bell curve, and in fact that's approximately 95%. So 95 of Batmobile lifespans should fall between 5 years and 15 years. So approximately 95% of Batmobiles have a lifespan between 5 years and 13 years. And if we move forward that third standard deviation and back up a third standard deviation, we talk about being that area that's between them. We're now covering most of our bell curve, and in fact, we're talking about 99.7% of all of our data is going to be trapped between those values, so between 3 and 15. So we could write approximately 99.7% of all Batmobiles have a lifespan between 3 years and 15 years. This is just a straight interpretation of the empirical rule. You can talk about being outside those values, and because the entire data is being represented under the curve, which is 100%, we could actually work with that idea. So if we were to examine one standard deviation above and below the mean, so our 9 years is in the middle, that's our mean. We moved one standard deviation above, we were at 11 years. We moved one standard deviation below, we were at 7 years. We know that the amount of data that falls between those is 68%, approximately. Well, even though my graph doesn't look symmetric, it's supposed to be. It's the downfall of trying to draw these by hand. If the entire set of data under the curve is being represented, which is 100%, we could figure out how much data is in what we call the tails. You have to have all your data represented, so if 68% of your data is in the middle, if we take 100 and subtract 68%, that's going to leave us with 32%. 32% has to be the amount that's left over in both of the tails, because it has to, again, add up to 100%. So if I wanted to just calculate how much area is in just a single tail, I would, because of symmetry, know that half of the data has to be in the right tail and half of the data has to balance that in the left tail. So if I take 32 and divide it by 2, I'm going to get 16%. And that's how much area is in each of the tails. So I'd have 16% of my data here, and I'd have 16% of my data on the left. So I could interpret that component, that percent, with the 11 years. To the right of a number means you're more than in value. And so we could say that 16% of Batmobiles have a lifespan greater than 11 years. Or 16% of Batmobiles have a lifespan that's less than 7 years. You can do that type of splitting of the tails and talking about being above and below certain value with each of the different empirical rule steps. So we could again write that 16% of Batmobiles have a lifespan, and we could write one of two things, 11 years or more, or higher, whichever wording you prefer, or we could write 7 years or less. You can also use phrases like at least or at most, so at least 11-year lifespan or at most a 7-year lifespan. At least implies greater than or equal to. At most implies less than or equal to. And that's the empirical rule and some of the different things that you can do with it when talking about data that's normally distributed. That means bell-shaped and symmetric.